Hello, it's probably only going to be Mr. Durant watching this, but I'm just going to pretend like these are multiple people. So I'm doing a 5.3 applications of exponential functions. The first thing I want to cover is that there's two main exponential functions: exponential decay, which is this red one, and exponential growth, which is this blue one. Now, what makes exponential decay or exponential growth is if the rate is greater than 1, then it's exponential growth. If it's lower than 1, then it's exponential decay. This formula for compound interest, it doesn't really, well, it's not really meant for exponential decay, even though I'm sure you could plug something in here. But yeah, it's mainly meant for like only exponential growth. This compound interest formula is the main formula that we're going to be using for all of the growth, and then we're going to have the special half-life for exponential decay. Okay, now excuse this. So exponential decay, the isotope barium-137M has a half-life of 2.6 minutes. How much of a 5 kilogram sample will be left after scientists conducts a 30-minute experiment on its luminescence? So first we need to pull up this. So oops, 1 second, my bad. That's distracting. So this formula, A equals P times 0.5 to the x over h. So A is the final amount, P is the initial amount, 0.5, that's just symbolizing this is how long it takes for half of it to disappear. And then x over h, x is the time, so that'd be 30 minutes, and then h is the half-life of this substance, and for this example it's 2.6 minutes. And the initial amount, it would be 5 kilograms, so that would be P. First let's plug everything in. Here we go. So 5 times 0.5, 30 over to the 30 over 2.6 power. If you plug that into your calculator, you'll be left with a number that's about 0.002 grams, and since we're using metric, let's just take it a step further and make that 2 milligrams. Yep, that's it for this exponential decay. Exponential growth now. I'm sorry about this again. I didn't really check the size of the screen first. So a gaggle of 15 geese wander into a Beastie Boys concert and are overwhelmed with the testosterone. If the testosterone increase causes them to reproduce at a rate of 33% every month, how many geese are present after 5 months? So we're going to use this population formula, which is A equals P times X to the X power. So what does this formula mean? A stands for the final population, P is the initial population, A is the rate, which if we go back to this compound interest, the rate is actually 1 plus the actual rate, and then X is the number of times it's compounded. So let's separate this into the problem. So let's plug this into the problem. So 15 is our starting number of geese, and our rate is 33%, so we turn that into a 0.33% and then add that to 1, so 1.33, and then the number of times it's compounded is 5 months, since this is 33% every month, so that's 5 months, and all we need to do now is just plug it in, and we're left with 62.4 geese, which is roughly 62 geese. Okay, oh, 1 second. Okay. Now, finally, we're gonna do a real life application. So money. So you invest $420 into a bank account that you can't access for 5 years. After the 5 years are over, you are left with $500. What was the rate of change? So this is an example where you have to kind of play around a little bit with the numbers. So we can plug in a lot of this stuff, but we don't have the rate. We don't have the actual rate. We're trying to find the rate. So let's just plug in what we have right now. That's $500 equals A. $420 is the starting amount, and then we're going to compound that over 5 years. So first step, we're gonna divide both by 420, both sides by 420, and then that's going to come out to, oh, sorry about that. That's going to come out to roughly 1.1905 equals x to the 5th power. And then we're just going to do 1.1905 to the 1/5 power. And from there, we're left with 0.2%. So if we were to plug that back into this format, it would be 1.2. So the R would be 0.2. Yep, those are some applications of exponential functions. I hope you learned something. You probably didn't, because this is probably just Durant watching this, but have a good day.